Today's notes are on gas stoichiometry. So we'll be taking what we've learned from the gas laws, mostly the ideal gas law, and applying that to what we learned in our past unit of stoichiometry. So the best way to do this is through a bunch of examples. The first example, using the equation that we're given, what volume of oxygen will be produced from 10.5 grams of KClO3 at 1 atmosphere of pressure and 25 degrees Celsius. So we're going to be looking for volume of oxygen, and we're given 10.5 grams. We're also given 1 atm and 25 degrees Celsius. Well, if we look at volume, atmospheres, and 25 degrees Celsius, this all looks like things that would be going into pivnert. The 10.5 grams, because it's a mass, can't go into pivnert. And it's also 10.5 grams of KClO3. And we're looking for volume of oxygen. What that tells me is that we need to start with our 10.5 grams of KClO3, use stoichiometry to get to moles of oxygen, and then use moles of oxygen in pivnert. So that's exactly what we're going to do. We're going to start with our 10.5 grams of potassium chlorate. And convert that to moles of potassium chlorate. And the molar mass of potassium chlorate is 122.55 grams. And then we're going to go from moles of potassium chlorate, and we're going to change that to moles of oxygen. And we know that there are 3 moles of oxygen and 2 moles of KClO3. And we're going to cancel out our units that cancel out. And we are left with moles of oxygen. And when we put those numbers into a calculator, we get 0.129 moles of oxygen. Now we're going to take our moles of oxygen and we're going to plug that into pivnert to solve for volume. So we know that PV equals nRT, and we're looking for volume, so I'm going to divide by pressure to get volume by itself. So V is equal to nRT over P, which our moles is now 0.129 moles of oxygen. Our universal gas constant is still 0.0821 liters times atms over moles times Kelvin. And our temperature is 25 degrees Celsius. Well, we know that we can't put 25 degrees Celsius into our gas laws, so we need to change that to Kelvin. So we're going to add 273, and we will get 298 Kelvin when we do that. So we're going to put in 298 Kelvin, and we're going to divide that by the pressure that it gives us, and that pressure is 1.00 atms. So when we look at this, it looks like we're going to have 3 sig figs in our answer, and we get the volume is equal to 3.14 liters of oxygen. Okay, and we're going to move on to another example now. And when we look at this example, so we have 2C2H2 plus 10O2 goes to 2H2O and 4CO2. And because this looks like it's a combustion problem or a combustion reaction, we know that the water is in gas form there and the carbon dioxide is also in gas form. So we're looking for what volume of gas at STP, that's standard temperature and pressure, will be produced if 3.7 grams of C2H2 is burned. So we need to look, so given the information that we're given, again, we're looking for volume of gas. So this is total gas. This isn't just water or just carbon dioxide, it's total volume of gas. And we're looking for we have STP, we have 3.7 grams of C2H2. Well, we're going to start with the stoichiometry again. So we start with 3.7 grams of C2H2. I'm going to convert that to moles, so grams goes on the bottom, moles goes on the top, and next to grams, the molar mass is 26.04 grams per 1 mole of C2H2. And then we know that there are 2 moles of C2H2 for every 2 moles of water. And so we need to convert to moles of water, and we need to convert to moles of carbon dioxide. So it's 2 separate calculations. When we convert to the moles of water, we end up with 0.14 moles of water. Then we need to do the same thing for the carbon dioxide. So we're going to start with our 3.7 grams of C2H2 again. And it's still 1 mole of C2H2 for 26.04 grams. And then we have 4 moles of CO2 for every 2 moles of C2H2, which then will give us 0.28 moles of carbon dioxide. So we're going to add these 2 moles together to get our total moles of gas. So when we do that, we get 0.42 moles of gas total. Then we're going to use this 0.42 to put into our pivnert. So we have PV equals nRT. And again, we're looking for V, so we're going to divide by P on both sides to get V equals nRT over P. And we're going to start plugging information in. So our volume is equal to 0.42 moles of gas times a universal gas constant of 0.0821 liters times ATMs over moles Kelvin times our temperature. It's at standard temperature now, so that's 273 Kelvin, divided by our standard pressure, which will be 1.00 ATMs. And when we multiply all of that out, we should end up with 9.4 liters of gas. Okay, now we're going to get things will get a little bit more complicated with this next concept. So the next concept is taking gas density and molar mass and combining them and putting them into an equation with the ideal gas law. So we'll start off with just talking about molar mass. Reminder that the units for that are actually grams per mole. So what that means is that equals our mass over our moles. So when we put that into variables, we have a little m for mass and an n for moles. And then also kind of do the same thing with density. Density is mass divided by volume. So that means that we have m divided by volume. And we know that the ideal gas law is PV equals nRT. So now how do we take these 3 equations and manipulate them so that we can stick them all into one equation? Well, let's start off with getting the molar mass and the density into one equation. So they both have mass as a common factor in them. So molar mass is abbreviated big M as a capital M. And that equals little m over n. So we're going to put this into and solve for little m so we can put it into the density equation. So little m is equal to big M times n. So now we can put in to our density, we can put this into our density equation right here, which gives us density is equal to big M times N divided by V. Now, in our, what do we have in this new density equation that we also have in our ideal gas law? Well, we have N and we have V. So if we can get N and V onto the same side of the equation and by themselves, then that allows us to put density and molar mass both into our ideal gas law. So to do that, we're going to divide both sides by big M, and that will give us D over big M is equal to N over V. So now we have to get, in this equation, we have to put N and V on the same side of the equation. And we need it to be N over V so that we can just plug this right in. So what that means is that we need to get V over on the left side, or from the left side over to the right side. So we're going to divide by V on both sides. So we have P equals nRT over V. Now we want to get rid of the R and the T. So we're going to divide both sides by R times T. So now P over RT is equal to N over V, which means now I can plug this in for this. So that means P over RT is equal to density over molar mass. So now we have a new equation that we can use. And we're going to use that in just a minute in our next examples. So determine the density of chlorine gas at 3 atms and negative 30 degrees Celsius. So we're going to use the equation that we just came up with, and that is P over RT equals density over molar mass. So we're going to have we're looking for density of chlorine gas at 3 atms and negative 30 degrees Celsius. Well, we need to change the negative 30 degrees Celsius into Kelvin. So temperature is equal to negative 30 plus 273, which is equal to 243 Kelvin. And everything else we can just pretty much plug right in. So the pressure we know is 3.00 atms. We know the R is 0.0821 liters atms over moles Kelvin. And the temperature is 243 Kelvin. That equals, we're looking for density, so we're going to leave the D there. And the molar mass of chlorine, well, we know chlorine gas is Cl2. We know that each chlorine weighs 35.45, so that's going to give us 70.90 grams per mole. So to get the density by itself, we need to multiply both sides by 70.90 grams per mole. So those completely cancel out. And then our units that cancel out, well, our ATMs cancel out here. Our liters stay there. Our moles cancel out here. And our kelvins cancel out. So when we multiply all of this out, we get density is equal to 70.90 times 3 divided by 0.0821 divided by 243. And when we punch all that into our calculator, we should get 10.7, and then our units are grams divided by liters. And there's our answer. Now on to one more example. This time, in this example, we're going to be solving for the molar mass instead when we're given a mass, a volume, a temperature, and a pressure. So we're still going to be using the exact same equation of the pressure over RT is equal to density over molar mass. But this time we're solving for molar mass. So it's going to be easier to manipulate this in variable form. So we're going to start out by cross multiplying and dividing. So we multiply these, and we multiply these. So when we first multiply these out, we get pressure times molar mass is equal to density times the universal gas constant times temperature. Now we're going to divide by pressure on both sides. And we get that the molar mass is equal to density times the universal gas constant times temperature over pressure. Now we're going to plug things in. But wait, we're not given a density. But we know the density is equal to mass over volume. So we're going to take the mass of 18.3 grams. We're going to divide that by our 12.2 liters. And that's going to give us 1.50 grams per liter. Now we can plug this into our new equation. So the molar mass is equal to the density, so 1.50 grams per liter, times our universal gas constant of 0.0821 liters times ATMs over moles Kelvin times the temperature. Oh, we got to change that too. So temperature is 90 degrees Celsius plus 273 Kelvin to change it into Kelvin, and we get 363 Kelvin. So that's 363 Kelvin divided by our pressure, which is 0.53 ATMs. Now let's check our units to make sure everything cancels out. Atmospheres cancels out. Liters cancels out. Kelvins cancel out. We're left with grams over moles, which is exactly what we want when we're solving for molar mass. And so when we punch all of the numbers into our calculator, we should get 84.3 grams per mole. And there's our answer. If you have any questions, please feel free to rewatch the video, and hopefully that will answer any questions that you have or ask your classmates. And good luck with your calculations.